Right now, somewhere in the universe, a giant star is detonating, creating a huge cosmic explosion called a supernova.
Supernovas are a big, giant, dramatic end to a star's life.
All stars die, but only the biggest go out with a bang.
For a star to go supernova, we think it has to be at least 8 times more massive than our sun.
It's so easy to think of our sun as this incredibly gigantic thing. But our sun is absolutely tiny compared to some of the giant stars in the sky.
We can see some of these giant stars with the naked eye. And the 10th brightest in the night sky is a red supergiant, around 15 times the mass of the sun. Betelgeuse.
Betelgeuse is so big that if you were to place it in our own solar system, it would stretch to the orbit of Jupiter.
This is one of the biggest beasts in the galaxy. It's a star also that is on the verge of death.
Betelgeuse is less than 10 million years old. But this huge star's days are numbered. It's ready to blow. And when it does, we'll see a region of sky brighten for 14 days until it's nearly as bright as a full moon.
It is going to be one of the most spectacular shows in history. And it could happen at any moment. I mean, this is the thing. I often stand outside in my yard in the wintertime. I look up at Orion and I see Betelgeuse, and I'm like, explode!
So, what will make Betelgeuse go supernova? To understand a giant star's death, we need to understand its life. From the day it's born until the day it dies, a star's life is a constant battle. Gravity is pulling in and energy pushing out.
The interior of a star is fusing countless atomic nuclei together.
Atoms are ramming into each other, getting very, very close. And if they get close enough, they'll actually stick and form a larger atom.
Every second, a giant star fuses 7.5 billion tons of hydrogen.
That amount of energy is roughly equivalent to about 100 billion atomic bombs per second.
That's a big-ass explosion.
This explosive energy threatens to blow the star apart. But the star's own massive gravity keeps the lid on.
Everything in the universe is a fight between the inward force of gravity and the outward force of pressure or energy.
Every single star in the sky, even our own sun, is an incredibly dynamic battleground. In many ways, stars are an explosion that are actually too big to explode. Gravity holds it together.
This battle between these two opposing forces determines the life and death of the star. And this is where size matters. The more massive the star, the more gravity pushes inward, and the harder the star has to push outward to keep itself alive.
Very massive stars are like stars on steroids. They have a lot of fuel to burn. They're so powerful that they use up their fuel at a rapid rate.
Massive stars, like Betelgeuse, are giant factories, fusing lighter elements into heavier ones. But the hard work doesn't start until their final years. For around 90% of their life, they fuse hydrogen into helium, but eventually, the hydrogen starts running out.
In the core of a supergiant star, there's a sequence of fusion that goes from lighter elements to heavier elements, and it gets faster and faster every step of the way.
The countdown to death begins. The inward push from gravity takes over, raising the temperature in the core. Helium starts fusing into carbon. There's enough helium to last about 1 million years, but it too runs out and things start speeding up.
Carbon gets fused into neon. That takes about 1,000 years. Neon fusing into silicon, that takes about 1 year. Once it starts fusing silicon into iron, that takes 1 day. It gets more and more frantic. It's kind of like a cooking contest show, whereas the clock is running down, they're trying to do more and more things, and they get more and more frantic until, ding, time's up.
The star is now in its death throes.
Once iron production has started, the clock is ticking towards the cataclysmic end of this star.
A giant ball of incredibly dense iron forms in the middle of the dying star's core. This iron sphere is several thousand miles across and unbelievably hot.
It gets so hot there, the temperature almost becomes meaningless. I mean, we're talking about 1 billion degrees in the center of one of these stars.
This extreme heat is caused by fusion reactions. More and more reactions create heavier and heavier elements, and with each step, less and less energy is produced until iron is created.
When you try to fuse iron nuclei together, that takes energy. It doesn't generate energy. So once the core starts to fuse iron, it's basically stealing its own energy.
The growing iron core sucks more and more energy from the star. Gravity continues pulling in, overwhelming the outward pressure from inside the star.
Everything gets crushed to unimaginable degrees. All of a sudden, there's no nuclear reaction to support the star against the crush of gravity.
With nothing left holding it up, the star is doomed. Gravity wins. The edges of the iron core collapse. Trillions of tons of dense iron fall inward at 1/4 of the speed of light. The star has now less than 1 second left to live. Things start to fall apart really quickly.
The core collapse is so fast that the outer layers of the star don't even have time to react. They're just hanging there. It's kind of like Wile E. Coyote when a cliff collapses underneath him and he doesn't even fall until he notices.
The rest of the star collapses. 1 trillion tons of gas hurtle inwards, following the iron.
Think about the entire mass of a star that has been held up by nuclear reactions inside. All of a sudden, those nuclear reactions go away in a split second. Everything rushes into the middle. And that sets off the most dramatic explosion in the universe.
The spectacular death blow can outshine all of the stars in the galaxy. But there's a problem. We still don't fully understand how a collapsing ball of iron and tons of falling gas create a giant fireball.
How this collapsing core triggers a massive explosion is one of the biggest mysteries in astrophysics.